All right, lesson 3.2 on linear functions. Some important vocab for today. A linear function is a function whose graph is a non-vertical line. So a straight line, not up and down. It also has a constant rate of change. All right, so if a linear function is a straight line, a nonlinear function is a function whose graph is not a line. It does not have a constant rate of change. And a linear equation in two variables can be written in the form y equals mx plus b, where m and b are constants. The important thing to know here is linear functions can be written y equals mx plus b. And then the solution of a linear equation is an ordered pair. All right, so example 1, does the graph represent a linear or nonlinear function? Well, part A is not a straight line, so we're going to say nonlinear. And part B is a straight line, so we'll say linear. All right, example 2, does the table represent a linear or nonlinear function? It's a little trickier when we're looking at input-output tables because we're looking at the constant rate of change. Remember, a linear function has a constant rate of change. So I look at my x values. How did we get from 3 to 6? We added 3, and that's also true for 6 to 9 and 9 to 12. And then how do we get from 36 to 30 in y? We went down 6. 30 to 24, we went down 6. 24 to 18, we went down 6. Notice that it's changing consistently. It has a constant rate of change. So part A is a linear function. Now part B, we look at our change in x from 1 to 3, it went up 2, 3 to 5, up 2, 5 to 7, up 2. Looks consistent for x. Let's check the y. From 2 to 9, we went up 7. From 9 to 20, we went up 11. From 20 to 35, we went up 15. This is not a constant rate of change, so this is non-linear. All right, example 3, does the equation represent a linear or nonlinear function? Remember in our vocab, we said a linear function in two variables should look like y equals mx plus b. We'll get more into what m and b are in the next lesson, actually. But they're both constants, meaning they're numbers. X can't be squared. So let's see, part A, y equals x plus 9. This could be 1x plus 9. We're going to say, yes, that's linear, because it looks like the form y equals mx plus b. Now, b is a little trickier. Y equals 3x over 5. We could also write this as y equals 3/5 x plus 0, which then looks like our mx plus b. M is 3/5, 0 is b. So yes, B is linear. And C, I noticed right away that we have an x squared. If x has an exponent, it's non-linear. So when you have an equation and you're looking to see if it's linear or not, notice if there's an exponent. If there is, it's non-linear. Now, before we go on to the next example, let's review a little bit from what we learned in 3.1. Remember, a function can be represented as an input-output table, a mapping diagram, a graph, or an equation. So there's multiple ways to represent a function. Remember, a function is when a relation has each input paired with exactly one output. So x cannot repeat. And then when we were looking at domain and range, remember domain is the x values and range is the y values. A domain is discrete if it's only certain numbers. When we were looking at it in 3.1, those were listed out, and then a continuous is when it consists of all numbers in an interval. This was the inequality. So if we were to write the domain for this bottom number line, we would say 1 is less than or equal to x, which is less than or equal to 5. Versus in the discrete domain, we just list out 1, 2, 3, 4, 5. It can't be between those numbers, it has to be exactly those numbers. All right, so example 4, problem solving. The linear function y equals 15.95x represents the cost, y, in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. Find the domain of the function. Okay, so first we're going to think, is the domain discrete or continuous? What is the domain? The domain is X. Can you buy half of a ticket? No, you cannot. So the domain is discrete, and the maximum of tickets you can buy is 4. You could buy 0 tickets. You could buy 1, 2, 3. Your maximum is 4. So the domain is 0, 1, 2, 3, 4. All right, part B, we're going to graph the function using the domain. So to do this, we're going to set up an XY table. And we already know X can be 0, 1, 2, 3, 4. We're going to plug in those values for X to the function that they give us up here to find our values for Y. Now I want you to pause the video for a second, fill in the numbers yourself. You should be doing notes either on your iPad with the PDF on Canvas or in Notebook. So pause the video, finish the XY table yourself. All right, and once you have the XY table complete, plot those points on the graph to the right. Pause the video for a second, fill those out yourself. All right, I counted by 5s on the y-axis, so for that last point, 63.8, I went a little bit off. That's okay. If you counted your y-axis by 10s, yours will be on the graph. I'm guessing you did not use 1s because that would not work in this case. Notice that it's discrete data. They are only points. The domain and range would be listed out. It's also a linear function because it passes the vertical line test. All right, example 5, it's going to look a little similar to example 4. A cereal bar contains 130 calories. The number C of calories consumed is a function of the number B bars eaten. That means C is dependent on B, so calories is your dependent variable, bars is your independent variable. Calories is Y, bars is X. Does the situation represent a linear function? Yes, because we have an independent variable, we have a dependent variable. The calories depends on the bars, and we can actually write this as, okay, a cereal bar contains 130 calories, so calories is going to be dependent on 130b, or 130 times the number of bars you eat. So find the domain of the function. Is the domain discrete or continuous? You could eat half of a bar. You could take a bite of a bar. So it could be continuous. You could argue for that. But we're going to say it's discrete and say that you can only eat a whole number of bars. So we're going to highlight discrete. Again, you could argue the other way. We're going to say discrete. Graph the function using its domain. I guess the domain would depend on how many bars you have. We're going to do an XY table. You could eat 0 bars. We'll say you should stop at 3. So 0, obviously if you eat 0 bars, you've had 0 calories. 1 bar will be 130 calories. 2 bars will be 260 calories. 3 bars will be 390. All right, so my x-axis is just going to count by 1s. And my y-axis will count by 50. So 200, 300. All right, so 0 bars was at 0 calories, 1 was at 130, 2 was at 260, 3 was at 390. And there is my function. This is linear, has a discrete domain. All right, some summary questions to wrap it up for today. What is a linear function? A linear function is a non-vertical straight line, passes the vertical line test to be a function, and then straight line linear. Linear functions are also written as y equals mx plus b. How is it different than a nonlinear function? Well, a nonlinear function is not a straight line. If you're given a table of values, how do you determine if the function is linear without graphing it? We're going to look at the constant rate of change for that. If the rate of change is constant in both x and y, it's linear. What is the difference between a discrete domain and a continuous domain? We looked at this in 3.1. Discrete is listed out. It can only be certain numbers in an interval. Continuous is an inequality, and it contains every number in an interval. How can you take a graph of a function and create a real-life situation from it? That was actually example 6 that we skipped, but we'll look at in class.